Good evening everyone. I am Manga from EC second year. I am from GPWM Badangpet College. So today's topic is 4-bit binary resistor method, DAC. So digital to analog conversion. So let us see what is digital to analog conversion. So let us consider a circuit called digital to analog converter. So the circuit looks like this, digital to analog converter. So here the input signals will be in the form of digital, D0, D1, D2 and D3. So these are the binary bits which is to be converted into analog form. So for digital to analog converter we have reference voltage. These reference voltage may be generated internally, or else we have to give this reference voltage to some ICs. Most of the ICs we have to give this reference voltage. So this is about digital to analog converter, which is to be converted into analog form. So let us come into binary weighted resistor method. So here we have the resistors. We have 3 stages in this circuit. So this is electronic switching network, and this is summing amplifier, summing network, and this is inverting amplifier. So these are the input binary bits which is to be converted into analog voltage. So here digital data input. So these bits are connected with respect to reference voltage. So here these bits must be converted into analog voltage. So these resistors represents the digital bit which is to be converted into analog voltage. Here the electronic switching network has 2 conditions. It means if this resistor reference is connected to binary bit, then it produces logic 1, or else if this reference voltage is connected to ground, then it produces logic 0. And here we have inverting amplifier. It means here inverting amplifier means it is in the form of negative feedback, and it produces a 180 degrees phase shift as it is an inverting amplifier. So let us consider the as it is negative feedback, so the concept called here we can apply the virtual short. So as virtual short, whatever the voltage which is present at inverting, whatever the voltage which is in the non-inverting op-amp, so it will appear at inverting terminal. So this is about virtual short. So here as node B, let us consider it is node B and node A. So whatever voltage which is present at non-inverting terminal, it appears at inverting terminal. So as here node B is ground, so it is VB is equals to 0. So VA also becomes 0. It means VA is equals to VB. So let us assume that the current which is flowing from these is IF. So here we are not connecting any direct ground, there is a virtual ground, so that the current will be flow from RF and output. So this is about the circuit diagram construction of a binary weighted resistor. Now let us see the derivation of it.
Good evening everyone. My name is E.Rakesh Goud. I am studying in Diploma second year from the Government Institute of Electronics. Okay, today I am going to derive the equation, derivation for the output voltage of digital to analog converter, which is a 4-bit weighted resistor. This is one of the method. Okay, now we will discuss about the derivation of the output voltage. First, let us see once again the circuit. Here we are applying node B. Here we have node B. Here node A. So if we apply KCL at node A, if we assume that if this is node A, this is the IF current. So if we apply KCL at node A, we will write output voltage is equals to minus RF into IF. This is the output voltage equation. How this is came? How the output voltage equation came? If we take the circuit, this is an inverting amplifier. So if we look at the figure, this is an op amp with negative terminal, positive terminal. This is ground, connected to the ground. This is node VB. This is node A. It is physical, it is not a physical ground, it is a virtual ground. So next, this is a resistor RF, which is a feedback resistor. This is the output voltage. This is RF. If we apply KVL at node A to this circuit, the current IF will flow through this RF resistor. Why it will not flow through the, already it is connected, it is physical ground, it is not physical ground, it is virtual ground. If we assume, if it is already it is not a physical ground, so that only purpose it is going to the RF resistor. Current will flow through only physical ground, not the virtual ground. So the current will flow, IF current will flow through the RF resistor and to the output voltage. So this is a non-inverting operational amplifier. So the output voltage can be written as output voltage is equals to minus RF into IF. How it came? By applying the KCL at node A. What is the KCL? The sum of the algebraic sum of the voltage across a closed loop is 0. So if we apply KVL at this node equation, we will get plus RF into IF plus output voltage is equals to 0, or else minus RF into IF minus V0 is equals to 0. From these both equations, these two equations can be written. So from either this equation or this equation, we can write the output voltage as minus RF into IF. So now what we have to do is, we have to find the IF current. We have to find the IF current, which is the, what is IF current? The IF current is the total combination of the flowing through this current 2 power 0 R and 2 power 1 R, 2 power 2 R, 2 power 3 R. The currents flowing through these lines to these lines, the total value of this current is called as the IF current. So what are the currents flowing through these resistors? For B0 bit, the current B reference voltage, the current flowing is I0, I1, I2, I3. So what is the value of the IF current? It is the sum of the I0 current, I1 current, I2 current and I3 current. Okay. Next. Now we will see, we have to find the IF current. What is the value of IF current? IF current is a sum of I0 current plus I1 current plus I2 current plus I3 current. So this is the sum of, what is the value of the IF current? I0 plus I1 plus I2 plus I3. I0 plus I1 plus I2 plus I3. This is the total values of the current, which is a sum. The value is IF. The IF current is flowing through the feedback resistor and going to the output voltage. So we have to find the IF current value. So what is the I0? What is the value of I0 current? I0 current is a current flowing through the 2 power 3 R resistor, which has some weighted value. So the current flowing through this resistor is the I0. So, and one thing, next thing, this is a reference voltage, right? This is a reference voltage. Next, what is the voltage present at these nodes? 0, because this is the reference voltage, this is the 0, as we have applied virtual short circuit. Because of negative feedback, we have applied virtual short circuit. So current node voltage at this 0 is equals to 0. So what is the voltage at this 0? So as it is 0 volts, we apply both 0 volts at all these terminals. So next one circuit. Before finding the I0 current, we have to look at one thing. This is the V1 voltage, this is the V2, this is the resistor R, this is the current I. For finding I flowing through this resistor, we have to apply one small formula, that is current I is equals to, already we know that by Ohm's law I is equals to V by R. So I is equals to V by R. What is the voltage at this equation? Here we have two voltages, V1 and V2. So we have to subtract V1 minus V2 by R is the voltage present or else flowing through this network. Okay, so same scenario or same principle is applied to this I0 current finding also. Next, I0 current means what is the voltage at this reference voltage? Minus 0 volts. By what is the resistance value? 2 power 0 R. So for I3 it is V reference minus 0 by 2 power 0 R. Next, what is the value? I0. So I0 means V reference minus 0 by 2 power 3 R. So I0 means what? V reference voltage minus 0 by, what is the resistance value? 2 power 3 R, plus what is I1 current? V reference minus 0 by 2 power 2 R. V reference minus 0 by 2 power 2 R, plus what is I2 current? I2 current is flowing through the 2 power 1 weighted resistor. So next, V reference minus 0 volts. What is I2 current? So V reference minus 0 volts by 2 power 1 R. V reference minus 0 by 2 power 1 R. Next, plus what is the value of the I3 current? I3 current is flowing through the 2 power 0 R resistor. So V reference minus 0 by 2 power 0 R. V reference minus 0 by 2 power 0 R. This is the value of the IF current. Next, we have to derive some of the equations, we have to derive clearly. Here 0 means we neglect it, 0 voltage is neglected. So V reference by R, it is a common from all the terms I1 naught, I1, I2 and I3. The common term is V reference by R. So we take the V reference by R from output of the brackets. Next, in the brackets we write that, before writing that, we will apply, we know that there are 4 switches, B0, B1, B2 and B3. We have to multiply with the above written equation, because the switch may be connected to the ground or else V reference voltage. So we have to multiply it with it. V reference into B, this is 2 power 3, B0, B1, B2 and B3. So if we take V reference by R voltage outside, we will get B0 by 2 power 3 plus B1 by 2 power 2 plus B2 by 2 power 1 plus B3 by 2 power 0. This is the value after taking the V reference by R as from outside of the brackets. This is the value. Now we have to give a generalized equation for the values written in this inside the bracket in the summation form, because if we have to write this all the equations, it must be lengthy, so we have to convert it into some generalized form. In the generalized form, if you substitute any value of the number or else any value, we have to get it. So in that way we have to write the general equation. Next, how we have to write, just see. In the summation form we have to write it. Summation I is equals to 0 to n minus 1 Bi. Why we have to write Bi? Because we have B0, B1, B2, B3. To get these values, we have to write as Bi by 2 power n minus 1 minus I. This is the generalized equation for the values written in the bracket. Okay. Next, we have to find this. I have written this is a generalized equation, but you have to know, you may get doubt, if we substitute this in this equation we will get or not. So, for example, any value, your wish. For example, B0 by 2 power 3, we have to get from substituting this in this equation. So, for example, what is the I value here? 0. What is the I value? 0. So, if we substitute that, if we substitute here, summation I is equals to 0 to n minus 1. What is the value of I? 0. So, B power 0 by 2 power, how many number of bits input digital data we are taking? 4 bits. So, n is the number of bits which we are taking input side. So, n is equals to 4. So, 4 minus 1 minus, what is the value of I we have taken? 0. So, we have to substitute here 0. What we get? B0 by 2 power 4 minus 1? 2 power 3. And also 3 minus 0, 3 only. So, we will get 2 power 3. As we get this output equation, this is the correct equation. I have just cross checked it whether it will come or not. Next, this is the output equation. By using this equation, we can find the output voltage of the digital to analog converter in binary weighted resistor. Okay. Next, we will take this V reference voltage has different values. Next, it will by taking different references values, we can find the output voltage. What is the output voltage of DAC? What is the output? Is either in digital form or analog form? We will get in analog form. So, we have to find the output voltage. To find the output voltage, we have to find we have to assume some reference voltage what we have taken and or else apply to it. So, if we taken V reference some value, what the output voltage will get? We have to tabulate these values, what the input data, as it is 4 bits, 4 input data, we have to substitute 2 power 4. What is the value of 2 power 4? 16. So, as we 16 input binary data we have to take, and correspondingly the 16 voltages at the output we will get. So, for what input data, what output data we will get, just by drawing the tabulation forms and by substituting in this method, she will be this.
So, let us see the tabular form. So, as we know that 2 power 4, as we are taking the 4 bits, so 2 power 4 is 16. So, the combinations will be in the form of 16. So, let us consider 16 combinations. So, it is a digital input which is to be converted into analog voltage. So, by substituting these bits, we can obtain the analog voltage. So, how it is? Let us see. We know this formula. So let us assume that V reference is 2 and RF is equals to R. So as we know, the formula is V minus RF by R into V reference into B naught by 2 part 3 plus B1 by 2 part 2 plus B2 by 2 part 1 plus B3 by 2 part 0. So this is the formula. So we have assumed that V reference is 2 and RF is equals to R, it means 1 only now. So here minus RF by R, this minus indicates inverting terminal. So here let us substitute these values in the formula and let us obtain the analog voltage. So minus 2, as RF is equals to R, it is 1 means, so let it be like that only. So into B, I am considering the 0010 bit. So 0010, it means B0, B1, B2, B3. As we know the formula and substituting this in the formula. Now 0 by 2 power 3 plus 1 by 2 power 2 plus 0 by 2 power 1 plus 0 by 2 power 0. So minus 2 into 0 by anything is 0. So 0 plus 1 by 4 plus 0 plus 0. Minus 2 into 1 by 4. It means minus 2 by 4. So the output analog voltage is minus 0.5. So this is the output voltage. So let us take another example to understand this in deeply. So 0, 0, 1, 1, B0, B1, B2, B3. Substituting these values in the formula, previous formula only. So minus 2 is the reference voltage as we know previously, and RF is equals to R, and substituting these bits in the formula. So that 1 by 2 part 3 plus 1 by 2 part 2 plus 0 by 2 part 1 plus 0 by 2 part 0. So minus 2 into 1 by 8, 2 part 3 is 1 by 8, 2 part 4, 2 means 1 by 4, 0 by anything is 0 and 0. No? So minus 2 into, by taking this LCM, 4 plus 8 by 32 and minus 2 into 12 by 32, 116, 6, 8, 3. So minus 2 into 3 by 8, it means minus 6 by 8, right? So the output, it will be in the form of 0.75, minus 0.75. So if you see this condition and this condition, here we got minus 0.5 and here we got minus 7.5. So the difference of these two is 0.25. So we can say that it is a resolution. So we can say that it is a resolution of each bit is 0.25. Here we are considering the reference voltage as 2. So we are getting the difference is 0.25. If you take 3, if you take 4, then the output will be changes according to V reference. So let us substitute this all analog voltage in this tabular form. Difference of 0.25 means, similarly we have to do all these bits by substituting the values in the formula. Now 0.25 for this 0.5, here minus we have to keep because we are assuming these op-amp in inverting configuration. So this minus should be there. So 0.25, 0.5 minus 0.75 and this is 1 and minus 1.25 minus 1.5 minus 1.75 and this is 2 minus 2.25 minus 2.5, minus 2.75, minus 3, minus 3.25, minus 3.5, minus 3.75. So, by taking digital input in the form of binary, we are taking the analog voltage in the form of difference of 0.25. So, this difference we can say it as resolution. Okay. So, according to this we can see the graph. So, it will be continued.
Now we will discuss the graph. From the taking the digital input, different digital input data, we have to graph the output voltage. We have to see the what is the relation between the input digital data and output analog voltage. So, for different input data, we are getting different output voltage. We have to for every electronic device, we have to see the how it's working. Is it linearly going or else non-linearly? It is a linear device or else non-linear device. So, we have to look at the digital to analog converters graph also. Okay, now I will draw the graph, just see it. In the x-axis, we will take the digital input data. Okay. On the y-axis, we will take the analog output voltage. Okay. Now we will draw the values of 0, 0, 0 here. 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, here 1, 0, 0, 1, 0, 0, 1, and here we get 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. This is the last bit, 1, 1, 1. If we next, we have to write the analog output voltages. As she had said that what is the resolution of DAC? 0.25 volts. 0.25, what is the units? Volts. So, resolution is 0.25 volts. So, we have to write this 0.25 volts every increment, and we have to graph that. 0.25, 0.50, 0.75, 1, 1.25, 1.50, 1.75, 2, 2.25 volts, and 2.50, 2.75, 3, 3.25, 3.50, and at last 3.75. Now we have to take the reference voltage of 0. 0, 0, 0. If we take the input digital data, what we will get output analog voltage as 0. Right? After substituting, we will get 0. Next. If we take 0, 0, 0, 1 as input data, what we will get? 0.25 from the table. So, we have to draw like this. Next. So, if we take the reference voltage digital input data as 0001, we get 0.25. Next, if we take the 0010 as input data, what we will get? 0010 if we take, what we will get? 0 point, minus 0 point, leave it minus is nothing but is a phase shift because we used the inverting amplifier, so it produces a 180 degrees phase shifter. So now if we take the 0010, we will get 0.50. If we take 0011 has input data, what we will get? 0.75. Next, 0. Next, accordingly the input data is varied. We have to draw the square wave like signal. Okay. So this is a stepwise signal. What is this? What is the distance between this? We call it as step size. Step size. If we draw a curve, we will get like this. It is a linear. It is a digital to analog converter device. Which how the characteristics is varied means linearly the characteristics will be varied. So by taking different input data, we will get in the different output, and we have graphed this input data in the x-axis and the analog output voltage in the y-axis. For different values, we get different step sizes, and this step size will depend upon the resolution of the digital to analog converter. So we, how we adjusted the resolution, that will affect the graph values. So we have, according to our requirements, we have to adjust it. Next. Okay, this is the last final graph of the digital to analog converter. Next, this analog to digital to analog converter will have advantages and disadvantages, but mostly we will discuss about disadvantages only. If you see the circuit, if we go down through the LSB, for example, we are transmitting only 4 bits. If you are going to transmit, or if I have different 8-bit, 16-bit or 32-bit data, then the value of the resistance, LSB bit resistance should increase. So as we go down, means as the number of bits increases, the LSB value resistance will also increase. For example, if we take 4 bits, 4 bit, what is the LSB bit value? 2 power 3, 2 power 3 into R. If I want to transmit 64 bit of data, 2 power 63 R. So as we are transmitting more number of bits, the value of the LSB bit resistance also increase, which is very impractical. So by using, this is the main disadvantages. The designers also will not accept our order also, because for different value, for every bit of data, we need different value of resistors. As we have already seen, that is a binary weighted resistor. So every resistor has a value which is multiplied by the 2 power something, 2 power n, 2 power 1, 2 power 2, 2 power 3, 2 power 4, like that. As we go down, the number of value of the LSB bit resistance is also increases. Next, in the summing network, we use the different types of resistors. So output voltage we will not get accurate. If we want to get the accurate value, we have to fix our resistance value within the limited values. So as it is different values, the resistance values is varying. So the output voltage may not get accurate. And also, if we calculate the equivalent resistance of the circuit may not get some constant value. Every resistance circuit something, we will get the equivalent resistance as some value, but here we will not get. So what is the alternative of this circuit? We use R2R ladder network, where are only 2 resistors only present, so that the equivalent resistance is R. But here we cannot find the exact equivalent resistance. So this is the disadvantages. Next, so we use the R2R ladder network. These are the disadvantages. Next, if you see advantages, it is a simple circuit, easy to operate. These are the advantages of this circuit. Next, okay, finally disadvantages and advantages are completed. If we overview what is a digital to analog converter, We have seen the circuit diagram, output voltage equation. What is the output voltage equation? Output voltage equation is equals to minus RF by R into V reference voltage into summation of I is equals to 0, n minus 1, BI by 2 power n minus 1 minus I. This is the output voltage equation. Okay, this is the output voltage equation we have derived. Next, according to the digital input data, we have graphed the analog output voltage. Next thing, according the different input data and output voltage, we have drawn the graph also. So this is the overview of digital to analog converter. Thank you.